In this video, we're going to apply the unit circle to evaluating specific trig functions and those specific trig angles. Now keep in mind that the unit circle is limited in what we're allowed to use it for. Now right behind this paper, I do have the unit circle listed and drawn, but I'm probably not going to use it all that much. I'm going to focus on rebuilding the unit circle every single time I have to utilize it, because this might not be sitting in front of me every time I need to evaluate specific trig functions. So let's start with the first example, and let's start with a relatively basic one. I'm going to go ahead and start with the sine of, let's do 4 pi over 3. So if I'm looking for the sine of 4 pi over 3, in my mind, in the unit circle, now I don't like pi over 3's because that correlates, that pi over 3, if you recall, correlates to 60 degrees. And in the unit circle video for building it, I didn't use a 60-degree marker to count my dashes. So what I'm going to do is I'm going to go ahead and rebuild my unit circle. But when I rebuild it, remember, I build it with a 30-degree marker. So I'm going to go ahead and cut this thing, and I'm going to change it to be the sine of, well, I want pi over 6. I'm going to multiply the top and the bottom by 2, giving me 8 pi divided by 6. Anytime I look at a 60-degree marker or a pi over 3 marker, I'm going to convert it to pi over 6's or to 30 degrees, because I know how to efficiently count that way. So I want 8 pi over 6's. Now remember, anytime that we build the pi over 6's, we're always going to count first dash, last dash. We're not going to count this middle one. This middle one is the 45-degree marker. That one's not important. So first dash is 1 pi over 6, 2 pi over 6. Then we're going to count every axis, 3 pi over 6, then 4 pi over 6 and 5 pi over 6. There's 6 pi over 6. Now again, notice how we did this. We're skipping this middle dash. I'm going to go ahead and try and do that in there right there. We're skipping that middle dash. That middle dash doesn't belong for our counting system. 1, 2, 3, 4, 5, 6. Then I'm going to have 7. Then I'm going to have 8. This right here is my 8 pi over 6 marker. I'm going to write that down. That's 8 pi over 6. It's the same thing as 4 pi over 3. Now, if I can fill in this first quadrant, I don't need to fill in the rest of this unit circle to find out what that number is. Let me very carefully go ahead and identify what these values are here. I'm going to build this almost every single time. I know my x value is 1 here and a 0 here. I know my y value is a 1 here, while my x value is a 0 here. And I've got 1, 2, 3 dashes. I need to know what those 3 dashes are. If I can memorize those 3 dashes, then the rest of this unit circle is just going to fall into place for me. The way that I'm going to memorize those values is as follows. I know that I need to have a 1 over 2. I need to have a square root of 2 over 2. I need to have a square root of 3 over 2. And in reality, isn't just a square root of 4 over 2 just a value of 1? Is that not just a value of 1? And technically, if I put a 0 over 2 here, isn't that really just a value of 0? So if you look at this and you're very, very careful with it, you'll notice that this is technically the square root of 1 over 2 and the square root of 0 over 2. And this is really just the 1/2 value that we're looking at. And the values just increase appropriately. So if I start with the y value of 0, I should simply be counting up a 1/2, a radical 2 over 2, a radical 3 over 2, and I end at 1. And then I can count my x values backwards. So it's 0, 1/2, radical 2 over 2, and radical 3 over 2. I'm going to go ahead and show this on the unit circle. You'll notice very closely here that it's 0, 1/2, radical 2 over 2, radical 3 over 2, 1, and then I count backwards. 0, 1/2, radical 2 over 2, radical 3 over 2, technically radical 4 over 2, which is really just 1. So I can identify those values relatively quickly, and once I have those values relatively quickly identified, I'm going to focus on where does this dash sit. Well, it sits closer to the y-axis, so the one that's closest to the y-axis should be the one I should be focusing on. It shifts over to this location, and then it correlates down to this location. It's going to build me a nice little rectangle in this situation within that circle. And all of those specific x and y values are exactly the same. So this location right here is 1/2 and radical 3 over 2. The only difference between this location and this location is the positive and negatives. And in this location right here, I'm going to have a negative on the 1/2 and a negative on the radical 3 over 2. So if I want the sine of 4 pi over 3, which is the same as the sine of 8 pi over 6, I count the pi over 6 as 1, 2, 3, 4, 5, 6, 7, 8 right here. I find the y value, the negative radical 3 over 2, and the sine of 4 pi divided by 3 is the same thing as negative radical 3 over 2. Done. Yes, I know it seems like I did so much work here, but once you get the hang of this built right here, you more or less memorize how this is built, and you simply just roll with the counting, you identify the location, and you pinpoint which location you're working with in that first quadrant, and just correlate with the first, second, third, and fourth quadrants based on what they are numerically in terms of positive and negative. So let's look at another example. Let's do the secant of 17 pi over 6. I'm doing another pi over 6 measurement just to get the point across in regards to the way the situation works. Now again, if you're doing a number of these all at once, you can just go ahead and stick to using the same circle. I like to always, again, at least redraw my counting situation. So I'm counting 17 pi over 6s. 17 pi over 6s. So very carefully, that's the first one, that's the second one. Again, always the two further dashes, ignoring the middle one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Uh-oh, what do I do now? Well, I continue to count. It doesn't matter that I've passed 12. This thing can go cyclical on forever. Just like the periodic functions, they repeat themselves. So there's 12 pi over 6, 13, 14, 15, 16, 17. So I'm at this dash right here. This is 17 pi over 6. But I know that this dash correlates to this location right here. And based on the previous unit circle that I just drew, that correlates to that right there. If it correlates to this over here, I have radical 3 over 2 comma 1/2. And in this location, I know that my x's are negative, my y's are positive. So it's going to be a negative radical 3 over 2. Now, secant is not sine or cosine. We remember that this thing is technically the cosine of theta comma the sine of theta. So the question comes out with, well, how do I find secant? Well, this is where those identities from section 4.2 come into play. The secant of anything is equal to, I'm going to actually write it this way, is equal to 1 divided by the cosine of that anything. This is true based on the reciprocal identities, so that means that if I know what the cosine of anything is, I can do 1 over that. Well, in this case, the cosine is the x value in the unit circle, so this is equal to 1 divided by negative radical 3 over 2. If that's the case, I can go ahead and do a little bit of math magic here and do 2 over negative radical 3. It's really just simplification of numerical values using basic algebra skills. And then I go ahead and rationalize the denominator because I don't like radicals in the denominator. So I'm going to have, I also don't like the negative in the denominator, so I'm going to do negative 2 radical 3 divided by 3. Again, if you're struggling with rationalizing denominators, please look back at previous videos. It does show that step and that concept there. In this video, we're focusing on how do we use this unit circle. Again, how do we use this unit circle to evaluate what we're looking for? Well, you'll notice here, if we're sine or cosine, we're just picking x and y values in here, making sure that we know how to count so that we don't have to rebuild the entirety of the unit circle if the thing isn't sitting in front of us. For secant, cosecant, tangent, and cotangent, we're going to use either the reciprocal identities or the quotient identities in regards to finding out what the sine and cosine correlations are, and we're going to pick those directly out of the unit circle. So let's do one more example, then we'll go ahead and do at least one generalization based on the unit circle and what we can come to the conclusion to. The last example, let's go ahead and do a cotangent of, let's do a negative 3 pi over 4. Now again, remember with the negative angles, all we're doing is we're counting backwards. Now notice how in all three of these examples, I have done radian measures. Sure, you can use your degree measures, but no matter what I'm given, this being the cotangent of a negative, 135 degrees, I'm never going to use the degree measure. I think it's clunky, it's inconsistent, and it's uncomfortable to utilize. But in this negative 3 pi over 4, I can very easily, well, instead of counting 1, 2, 3, because that's wrong. I'm counting 1, 2, 3. Again, remember, pi over 4s count the middle dash. 45 degree measures count the middle dash. I don't want to count this way. It's a negative angle. I will always count clockwise if it's a negative angle. So I'm going to go 1, 2, 3. This is the location for negative 3 pi over 4. If I was doing 3 pi over 4, then I'd be over here. This is another reason why, again, I don't like degree measures, because you see that 135, you might think you're here just because you see the 135, and that's not true. You're down here. You're looking at a negative 135, which means that you have to go backwards to this location. And notice there are no negative angles written on this at all. Sure, you can fill them in if you'd like, but that's a lot more effort than you need, especially if you're going to use the radian measures in the grand scheme of counting anyways. I think counting is a lot easier than it is to add a bunch of relatively large numbers together that are arbitrary in regards to 360 degrees. So, I'm at this location. I know that this right here is radical 2 over 2 comma radical 2 over 2. This one's one that's really easy to memorize, so I'd just say memorize that one. The ones that you might get confused with are the 30s and the 60s, but again, the way that you remember is that this is the larger one, it decreases going up, and then the y value decreases coming back down. So, with that being stated, this location over here is negative radical 2 over 2 comma negative radical 2 over 2. Because it's positive x and y, and again, the decision of which one's positive and which one's negative is entirely based on the xy coordinate plane, not on the circle. So it's negative x, negative y. If I were to try and plot a point down here, it's negative x, then negative y. So they're both negative numbers, but they're both supposed to be symmetric to these 2 points right here. So if I'm looking for the cotangent of that location, the cotangent is the cosine of that value divided by the sine of that value. And therefore, if I take those two values in their appropriate order, cosine being the x number, negative radical 2 over 2, divided by the sine value, negative radical 2 over 2, yeah, I know they're both the same, this equals to a positive 1. So the cotangent of negative 3 pi over 4 ends up being 1. So, with that being said, let's do some slight generalizations based on the unit circle. We're going to do one more detail in this image right here, and it's going to be entirely based off of the trig functions and how we can define them. In this first quadrant, because x and y are both positive, we can look at the reciprocal and the quotient identities, and we can say that all trig functions are positive here, every single one of them. So if I talk about a sine function or a cosine function, a cosecant, secant, or cotangent, anything between 0 and 90 degrees, I can say that every single one of those values should spit back a positive number. In the second quadrant, notice here that I'm going to go backwards for x and upwards for y. So it's a negative x and a positive y. That means my cosine function is negative. My cosine function is negative. I'm going to do a real small cosine. But if my cosine function is negative, then its reciprocal is also negative, which means that the cosine is negative. I'm sorry, that's not what I want to write here. I want to write that the cosine function is negative, and therefore also is secant. So cosine is negative, secant is negative. But if these two functions are negative, if I try to do tangent or cotangent, those values are also going to be negative. So what I really want here is I want a capital S, because sine is what's positive. Notice how I wrote what was positive over here. All the functions are positive over here. Sine is positive over here, and its reciprocal function, cosecant, is positive over here. Because again, cosecant being the reciprocal of sine forces it to also be positive. So I have capital S, sine being positive here. Down here in the third quadrant, we're going to go ahead and have negative, negative. If it's negative x and negative y, the only function that can be positive is tangent and its reciprocal cotangent. Those are the only two functions that can be positive down here. So we put a capital T, and then over here, my cosine function, because it's a positive x and a negative y, my cosine function is what's positive down here with its reciprocal secant. So the mnemonic device, again going in 1, 2, 3, 4 order based on the appropriate order of your quadrant system, all students take calculus is the mnemonic device for memorizing which of the main 3 trig functions are positive, and therefore if we can remember that, we can then correlate the remembrance of the 3 main trig functions to their reciprocals. Again, students counts for sine, take stands for tangent, and calculus stands for cosine. So all students take calculus, all sine, tangent, cosine. We can better check some of the information about what's positive and what's negative where they occur. This allows us to better utilize this unit circle in a number of different ways. There is possibly more to this unit circle than we can potentially see just off the bat. And again, utilizing the counting functions to better evaluate these values here is just one way we can use this unit circle to the better of our advantage. If you don't want to use this unit circle, you don't have to. But I want to be very clear about this. If you're not using the unit circle, then you're using a bunch of table of values. And these table of values are not going to work cyclically for the larger angle measures that you're going to want to have to play with, especially for this one here, say the, again, 17 pi over 6, or this one here, working your counting angles backwards. They don't make any sense in a triangle. You can't use them in a triangle. That's where the unit circle is most important. That's how we utilize the unit circle.